Dear colleagues, I'd like to present our report, named Packing Equal Spheres by Means of the Block Coordinate Descent Method. Packing spheres consists to arrange equal or non-equal, non-overlapping spheres within a containing space, or into a larger three-dimensional domain, called a container. A typical objective is to fill as much of the space, or the container, as possible. The sphere packing problems are of interest in various subject areas, for example, in studying structure of crystals, liquids, glassy materials, catalysts, and fuel elements, etc. The packing density of equal spheres is a significant factor in the study of processes in thermal heat exchangers, chemical, and nuclear reactors. Well known are applications of packing spheres in medicine and engineering. The aim of the work is to develop a method of dense random packing a large number of equal spheres into a composed container, being a geometric model of a chemical reactor. The main tasks are analytical description of non-overlapping the spheres, and containment of the spheres in the container. Construction of a mathematical model. Development of a solution method to pack a large number of spheres. We deal with the problem of packing a large number of equal spheres into a container of sphericylindrical shape, with a cylindrical prohibition area which arises in chemical industry. The problem is presented as a mathematical programming problem, on the ground of the Stoyan's phi functions method. Solving the problem is reduced to solving a sequence of nonlinear programming problems, making use of the block coordinate descent method, and analysis of Lagrange multipliers, to realize sequential addition of spheres. Numerical examples for up to 2 millions of spheres are given. The problem is formulated as follows. One should pack the maximal number of spheres from the given set of spheres into the container, without overlappings, and calculate their center coordinates. A mathematical model of the problem is presented as a mathematical programming problem, with the piecewise constant objective function. The problem is multi-extremum. All local maxima being non-strict, due to the axial symmetry. In order to pack a large number of spheres, we make use the block coordinate descent method, thus realizing the sequential addition of spheres. The problem is reduced to solving a sequence of problems. On the first step, the first sphere is packed into the container, being located at a position with the minimum height. Then, this sphere is assumed to be immovable. On the next step, the second sphere is packed into the container, the first one being immovable, and so on. At each step we search for a local minimum point for the auxiliary problem. If a feasible point of the auxiliary problem for some sphere cannot be found, then the solution of the previous problem solved is a solution of the main problem. The objective function being linear, minima are reached at extreme points of the feasible region. The algorithm consists of the following stages. Random choice of an initial point of the feasible region. Movement to the frontier of the feasible region, decreasing the objective. Movement on the frontier of the feasible region to an extreme point, decreasing the objective. Searching for an extreme point, being a local minimum point. To improve the value of the objective of the auxiliary problem, we realize the multi-start method on each step, and choose the best local minimum. In order to numerically test the packing approach proposed, we developed a software, and calculated several examples for different numbers of spheres, up to 2 million spheres. As experimental results show, the spheres forms regular structures along the frontier of the packing domain, that is the container wall. Conclusion. The problem of packing equal sphere into a bounded container is considered. The method suggested allow to solve the problem of large dimension. Due to applying the block coordinate descent method, which allow to reduce solving the problem to a sequence of nonlinear programming problems. The optimization method realizes search of a frontier point of the feasible region, then, an extreme point and step-by-step movement to a local minimum point. Choice of descent direction is defined by analyzing Lagrange multipliers corresponding to active constraints. Numerical examples show effectiveness of the method for up to 2 million equal spheres. The Stoyan's phi function method allows to adopt the developed method to pack spheres into containers of arbitrary spatial shapes. The method can be also extended to pack unequal spheres. That's all. Thank you for your attention.